for ANN as a regressor. ANN as a regressor. Then I will tell you what are all the changes in the gradient descent calculation when ANN as a classifier. Okay, both we are going to do. So ANN as a regressor, I have taken this example. So from the relationship, you can see it is a very strong linear relationship. Okay, for example, this is the units. Okay, 1 centimeter equivalent to 2 units will take 2, 4, 6, 8 in the x-axis, and the y-axis will take 1 centimeter equivalent to 5 units, 5, 10, 15, 20, like this. So what is the first pair of points I have to mark when x is 2, y is 5? So here, okay, when x is 5, y is 12. Y is 12 somewhere here. When x is 7, okay, and x is 7, if y is 15. Visually, it looks like all the points are lying on a straight line, but maybe, okay, very close to the straight line. If all the points are lying on the straight line, naturally your error will touch the 0. Okay, that's the point. Practically, your error will never touch 0. Of course, and this example is a linear example I have taken. The reason is still we have not introduced the hidden layer concept. So I can solve this using a simple input-output architecture without hidden layer architecture, like the way we have implemented yesterday, like a Rosenblatt learning process. Again, the notation here it is used as the standard linear regressor notation, but you can also follow your neural network notation for this case. Okay, we randomly initialize the initial weight of the bias is 1. Okay, the initial weight, because only one feature is involved, so I'll get only one weight associated. Okay, let me call that weight as W1. So the initial weight, or you can say the initial slope. Okay, we have only one slope, right? 2 features means 2 slope. Just for the simplicity for the handwork calculation, I have taken only one feature, and this is the weight of the bias. So the initial intercept is 1, and the initial slope is 3. I have taken randomly. After completing this session, because our next session we are going to meet only on the Saturday morning, right? In between, if you have a Friday, if you have a time and if you are interested, you can work out the same calculation with some other initialization. Okay, it's a very interesting calculation. It won't take more than 20, maximum 30 minutes. Just 15 to 20, or the worst case 30 minutes. But it's worth doing that calculation as a handwork calculation. So instead of this initial values, you can start with some other initial, but finally you will appreciate it, irrespective of my initial weight values, your end result, that means my error, how the error is going to get converged. That is the beauty of this gradient descent learning. So for the randomly initialized weight of the bias and the W1, what is our equation? Since neural network as a regressor, when the neural network behaves as a regressor, it just calculates only the net, right? WB plus W1x. It will calculate up to net. If you design neural network as a classifier, then for this net value, what we'll apply? 1 divided by 1 plus e to the power minus net. Okay. For time being, let us forget about this activation. So we have only net. So this output is basically, we are going to train the model towards the net value. Okay. So for the given randomly selected bias and weight, let me calculate what is my net. Okay, the net is nothing but, we'll understand it is a y cap, right? Basically, model is going to predict this value. So my y cap is nothing but WB plus W1x. Okay, so 1 plus 3x. Basically, this is initial value is 1, this initial value is 3. So basically, it is 1 plus 3x. So first I plug in 2 in this equation. Okay, x you substitute 2, 2 3 is 6, 6 plus 1 7. Then I plug in 5 in the equation. When x takes 5, 15 plus 1, 16. When x takes 7, okay, 21 plus 2, 20, 21, 22. This is the actual output. Okay, this is the actual output or desired. According to the neural network notation, we use desired output. And this one we call it as a O, right? D minus O the whole square. Okay, or y minus y cap the whole square. If you consider this as the y, or y minus y cap the whole square. So my SSE, you know what is SSE? SSE is nothing but we have defined 1 by 2 d minus O the whole square, isn't it? So this is d. In the bracket, I'll just write the neural network notation also. This is d, and this y cap is nothing but O. Okay, so d minus O. So 5 minus 7 whole square. So 5 minus 7 whole square scaled by 1 by 2. So yesterday I told you what is the significance of this 1 by 2 for the just for the mathematical convenience. Because we don't want to have, these are the error gradient term. Yesterday we computed the error gradient term. We got this relationship also. How do we got minus of d minus O for the bias? Okay, for the slope, what we got minus of d minus O times x1. But here also you can define as x. Make sure that you have to maintain x is 1. Okay, so I have substituted 1. That is why I'm not defining the x here. So since the x value is 1, so this is the error gradient term for the to adjust the bias. To adjust the slope, what is the error gradient term? Yesterday we derived this minus of d minus O times x1, or since we have only one feature, I can call it as x, or specifically if you wanted to call it as x1 also, you can call it as x1. So first I am calculating the individual, how each record is individually contributing to the total error, right? So how each record is individually contribute. So 5 minus 7 is minus 2 the whole square divided by 2, which is 4 divided by 2. So 2. Then we compute 12 minus 16 minus 4. Minus 4 whole square is 16 divided by 2. We got 8. Then 15 minus 22. The difference is minus 7. 7 square is 49. 49 by 2 is 24.5. Now total error is, sum of the error is 34.5. So if you look at the cost function, here our cost function is nothing but 1 by 2 d minus O whole square. It's a squared function. If you try to plot this cost function, this loss function, you will get a, because of squared term, you will get something like a circular for the different combination of d and O. You will get something like a convex shape you will get. And randomly we have taken for the randomly selected slope and intercept. What is the error we got? SSE 34.5. Let us mark somewhere 34.5 somewhere here. Initially we have randomly selected intercept and slope, which is WB and W1. For the randomly selected value, my initial error is somewhere higher value. Let us assume this is somewhere at higher value. What is our objective? Our objective is to minimize this error to, okay, we have to descend down this error towards the minimum value. So that is our objective. So if it is, I can adjust my weights in such a way that if I could reduce this error, means my model is approaching to the actual value. So that is the intention. Okay, to adjust, what is the formula to adjust the weight? Yesterday we have seen to adjust the bias, WB, okay, nu is equivalent to WB initial. Okay, I can call it as WB initial. So the general formula is minus of, okay, general formula is minus of eta times of dou E by dou WB. This is the general formula. Okay, this guy is, I have calculated here. What is dou E by dou WB? Yesterday we derived as minus of D minus. This is nothing but minus of D minus O or minus of Y minus Y cap. So I calculate the individual error gradients. What is actual Y? 5, and the predicted is 7. So the difference is 5 minus 7. 5 minus 7, we get minus 2, because yesterday we have, remember, the derivation has the negative sign also. So attaching the negative sign, minus of minus 2 become plus 2. Okay. Either you keep the formula plus here. If you already took this minus sign to this, minus of minus plus, here you have to represent y minus y cap as minus. Okay. Any one place you substitute, otherwise you'll get confused. So I wanted to make the formula as generalized. Yesterday in our Python coding, I have took that minus sign. So minus of minus, plus sign with the equation we have written as a plus sign. So W plus equivalent to plus eta times t minus O, we have substituted. So in this place I didn't introduce minus sign, because already I took this minus sign. So minus of minus, this plus sign we have got. So in the handover calculation, I wanted to show this portion explicitly based on the derivation how we got. I wanted to keep it like that manner. So the derivation yield minus of t minus O. So I keep this as minus of t minus O. Here the derivation yielded minus of t minus O times x. So here x is 1. So I have not shown that x explicitly. For the bias input, x is 1. So we compute the individual error gradients. So 5 minus 7 minus 2, minus of minus 2 plus 2. Similarly, 12 minus 16 minus 4, minus of minus 4 plus 4. 15 minus 22 minus 7, minus of minus 7 plus 7. So I calculate the total error gradients. Okay, this is the individual error gradients. I am calculating this. So error gradient can be shortly represented as, this is dou E by dou neural network notation, dou E by dou W, or dou E by dou beta naught. In linear regressor notation, you can use this neural network notation. This is okay. We are going to substitute this as the adjustment factor for your bias. Okay, WB new equivalent to WB initial. Okay, initial minus eta times of this value you are substituting, right? That means for the initialized, for the randomly selected bias or the randomly selected W1, you are going to provide some change here. Okay, so that change I can represent with something like this, delta WB. Okay, for the initialized, randomly initialized bias, you are going to give some change. So either you can call this as a dou E by dou WB. Shortly, you can call it as a delta beta naught or delta WB. That is why I have written this as a delta beta naught or delta beta 1. Here you can also write it as delta WB or delta W1 or delta W. So in the same manner, I compute the error gradient term for to adjust the slope. Also I compute. Only difference is this term you just multiply with your x. What is x? 2. So 2 into 2, 4 we got. This guy I should multiply with this x, 5. So we got 20. This guy I should multiply with this x, 7. We got 49. So I compute the total error gradient. This is summation of delta WB. This is summation of delta W1. So what we are going to substitute here in the formula is, there are different strategies are there. That is the towards the end of today's session, you will come to know that what are all the different strategy I can substitute this. Okay, there is no one fixed strategy.